ML isn't hard, but interviews are. Are you ready? What is an artificial neural network? Answer: an artificial neural network is a computer system inspired by the structure and function of the human brain. It is a network of interconnected nodes, called artificial neurons, that work together to process and learn from input data. The network is designed to mimic the way the human brain processes information, with layers of neurons that receive and transmit information to each other. The connections between neurons are weighted, meaning that the strength of the connection between two neurons can be adjusted to optimize the performance of the network. This allows the network to learn and improve its performance over time. Artificial neural networks are used in a wide range of applications, including image and speech recognition, natural language processing, and predictive modeling. How does deep learning differ from machine learning? Answer: deep learning is a subset of machine learning that uses artificial neural network architecture to learn the hidden patterns and relationships in a dataset. Unlike machine learning, which applies statistical algorithms to learn from the dataset, deep learning requires a larger volume of dataset and takes more time to train the model. Additionally, deep learning is better suited for complex tasks like image processing, natural language processing, etc., and can automatically extract relevant features from images, whereas machine learning relies on manually extracted features. As a result, deep learning models are more complex and difficult to interpret and require high-performance computing power with the GPU, whereas machine learning models can work on a CPU or with less computing power. Overall, deep learning is a more advanced and powerful approach to machine learning, but also more challenging to implement and interpret. What are the applications of deep learning? Answer: deep learning has several applications in various fields. It is used in computer vision for tasks such as image classification, image segmentation, object detection, and image generation. It also has applications in natural language processing, NLP for language modeling, sentiment analysis, and machine translation. Additionally, deep learning is used in reinforcement learning to enable agents to make better decisions and maximize rewards, which has applications in gaming, robotics, and control systems. Overall, deep learning has a wide range of applications that have improved the precision and effectiveness of various tasks and industries. What are the challenges in deep learning? Answer: deep learning has made significant advancements in various fields, but there are still some challenges that need to be addressed. One of the main challenges is the need for large amounts of label training data, which can be time-consuming and expensive to collect. Another challenge is the risk of overfitting, where the model becomes too specialized to the training data and fails to generalize well to new, unseen data. Additionally, deep learning models can be difficult to interpret and understand, making it challenging to identify the reasons behind their predictions. Furthermore, deep learning models can be vulnerable to adversarial attacks, where an attacker intentionally modifies the input data to deceive the model. Finally, deep learning models require significant computational resources and can be slow to train, which can be a challenge for large-scale applications. These challenges highlight the need for continued research and development in deep learning to overcome these limitations and improve its performance. What is a major concern when using deep learning, and why is it challenging to gather data for training? Answer: a major concern when using deep learning is data availability. This is because deep learning models require large amounts of data to learn from and improve their performance. Gathering such a large amount of data for training can be challenging, which makes data availability a big concern. This is because the more data the model has, the better it can learn and make accurate predictions. However, collecting and preparing large amounts of data can be time-consuming and expensive, making it a significant challenge in deep learning. Why is training a deep learning model computationally expensive? Answer: training a deep learning model is computationally expensive because it requires specialized hardware like graphics processing units GPU and tensor processing units TPU. These specialized hardware are designed to handle the complex mathematical calculations involved in deep learning, such as matrix multiplications and convolutional neural networks. The large amounts of data and complex algorithms used in deep learning models also require significant computational resources, making it necessary to use powerful hardware to train these models efficiently. What can cause a task to take a very long time to complete when working with sequential data, even using powerful computational resources? Answer: the task can take a very long time to complete when working with sequential data because the computational resource is limited, making it process the data slowly. This can result in the task taking days or even months to finish. This is often the case when dealing with large amounts of sequential data that require significant computational power to process. What is the main challenge in understanding the results of deep learning models, and why is it difficult to interpret their outputs? Answer: the main challenge is that deep learning models are complex and work like a black box, meaning that it is difficult to understand how they arrive at their outputs. This is because the models are composed of many layers of interconnected nodes, and the relationships between these nodes are not easily interpretable. As a result, it is challenging to identify the specific features or patterns in the input data that are contributing to the model's predictions, making it difficult to interpret the results. What happens to a model when it is trained repeatedly, leading to poor performance on new data? Answer: when a model is trained repeatedly, it becomes too specialized for the training data, resulting in overfitting. This means that the model is no longer able to generalize well to new unseen data, and its performance suffers as a result. In other words, the model becomes too good at fitting the training data, but this comes at the cost of its ability to adapt to new situations. This is a common problem in machine learning, and techniques such as regularization and early stopping are used to mitigate the effects of overfitting. What are the similarities between biological neurons and artificial neural networks in terms of structure, synapses, learning, and activation? Answer: biological neurons and artificial neural networks share similarities in their structure, synapses, learning, and activation processes. In terms of structure, both have input nodes, processing units, and output nodes. Synapses in biological neurons are similar to weights in artificial neural networks, connecting nodes and determining the strength of connections. Biological neurons learn through synaptic plasticity, while artificial neural networks learn through backpropagation, adjusting weights based on the difference between predicted and actual outputs. Finally, activation in biological neurons is similar to activation functions in artificial neural networks, mapping inputs to outputs. These similarities demonstrate the inspiration from biological neurons in the design of artificial neural networks. How is deep learning used in supervised, unsupervised, and reinforcement machine learning? Answer: deep learning is used in all three types of machine learning: supervised, unsupervised, and reinforcement. In supervised machine learning, deep learning algorithms like convolutional neural networks and recurrent neural networks are used to make predictions or classify data based on labeled datasets. In unsupervised machine learning, deep learning algorithms like autoencoders and generative models are used to discover patterns or cluster datasets without labeled targets. In reinforcement machine learning, deep learning algorithms like deep Q networks and deep deterministic policy gradient (DDPG) are used to learn policies that maximize a reward signal in an environment. Deep learning is used to process and analyze data in all three types of machine learning, allowing for more accurate and efficient results. What is a perceptron? Answer: a perceptron is a simple type of artificial neural network architecture that was introduced in the 1950s. It consists of a single layer of input nodes that are fully connected to a layer of output nodes. The perceptron can learn linearly separable patterns and uses a type of artificial neuron called a threshold logic unit (TLU). It computes the weighted sum of its inputs and applies a step function to compare it to a threshold, making it a simple and effective model for binary classification tasks. What is a multilayer perceptron (MLP) and how does it differ from a single-layer perceptron? Answer: a multilayer perceptron (MLP) is a type of neural network that consists of multiple layers of interconnected neurons, allowing it to process complex patterns in data. In contrast, a single-layer perceptron has only one layer of neurons and is limited to learning simple, linearly separable patterns. The key differences between the two are the architecture, complexity, learning algorithm, output, and applications. MLP have more layers, can learn non-linear patterns, use backpropagation for training, produce real-valued outputs, and are suitable for complex classification and regression tasks, whereas single-layer perceptrons are limited to simple linear classification tasks. What are feed-forward neural networks? Answer: a feed-forward neural network is a type of artificial neural network where information flows only in one direction from the input layer to the output layer without any feedback connections. This means that the data is processed in a series of layers, with each layer transforming the input data in some way until the final output is produced. Feed-forward neural networks are widely used for tasks such as image and speech recognition, and are particularly effective when the relationship between the input and output data is complex and nonlinear. During the training process, the weights and biases of the network are adjusted to minimize the error between the predicted output and the actual output, using a technique called backpropagation. This allows the network to learn and improve its performance over time. What is a GPU? Answer: a GPU, or Graphics Processing Unit, is a specialized electronic circuit designed to render graphics and images on a computer or digital device quickly and effectively. It was originally developed for use in video games and graphical applications, but has since grown in significance in fields like artificial intelligence, machine learning, and scientific research, where it is used to speed up computationally demanding tasks. One of its main benefits is its ability to perform parallel computation, using many processing cores to speed up complex calculations, making it particularly well suited for tasks like high-dimensional data manipulation and matrix operations. What are the different layers in an artificial neural network ANN, and how do we represent a node of a particular layer using annotation? Answer: an artificial neural network ANN typically consists of three types of layers: the input layer, hidden layers, and output layer. The input layer receives the input data and passes it on to the next layer. The hidden layers process the input data and transmit it to the output layer. The output layer produces the output of the network. To represent a node of a particular layer, we use a notation like NIL, where L denotes the layer number and I denotes the node's index inside that layer. For example, N0 represents the first node in the input layer, and N23 represents the second node in the third hidden layer. This notation helps us refer to specific nodes in the network to understand its structure. What is forward and backward propagation in deep learning and neural networks? Answer: forward propagation is the process where input data flows through the neural network, layer by layer, to produce an output. Backward propagation, also known as backpropagation, is the process where the generated output is compared to the actual output, and the error is measured and propagated backward through the network to update the weights and biases of each layer, allowing the network to improve its performance. In simple terms, forward pass involves feeding input data into the neural network to produce an output, while backward pass involves utilizing the output to compute the error and modify the network's weights and biases. What is the cost function in deep learning? Answer: the cost function, also known as the loss function or objective function, is a mathematical function used to measure the quality of prediction during training in deep neural networks. It calculates the differences between the predicted output and the actual output, and the goal is to minimize these differences by adjusting the weights and biases of the network using backpropagation algorithms. The cost function is used to evaluate the performance of the network and guide the training process. Different types of cost functions are used depending on the type of problem a neural network used, such as binary cross-entropy, categorical cross-entropy, sparse categorical cross-entropy, callback labor divergence, and mean-squared error. What are activation functions in deep learning and where are they used? Answer: activation functions in deep learning are mathematical operations that are performed on each neuron's output in a neural network to introduce nonlinearity. They take the output of the preceding linear operation and map it to a desired range, allowing the neural network to learn more complex relationships between input and output variables. Activation functions are used throughout the neural network, particularly during the forward pass to compute the output of each layer. They are also used during backpropagation to compute the gradients of the loss function with respect to the network weights. This enables the network to learn and optimize its weights to minimize the loss function. What are the different types of activation functions used in deep learning? Answer: in deep learning, several types of activation functions are used, each with its own strengths and weaknesses. Some of the most common activation functions include the sigmoid function, which maps any value between 0 and 1, and the ReLU rectified linear unit function, which outputs 0 for negative inputs and the input value for positive inputs. Other common activation functions include the tan function, which is similar to the sigmoid function but has a more symmetrical output, and the softmax function, which is used for output layers in classification problems. These activation functions help to introduce nonlinearity into the neural network, allowing it to learn more complex relationships between inputs and outputs. What is the main purpose of the softmax function in a neural network, and how does it differ from the sigmoid function? Answer: the softmax function is primarily used in multi-class classification problems where it maps the output of the preceding hidden layer into a probability distribution across the classes. This means it gives each class a probability value between 0 and 1, with the sum of the probabilities over all classes equal to 1. In contrast, the sigmoid function is used in binary classification problems where it maps the output into probability value between 0 and 1, but does not provide a probability distribution across multiple classes. The softmax function is an extension of the sigmoid function, allowing it to handle multiple classes in a single output layer. What is the difference between ReLU and leaky ReLU functions in deep neural networks? Answer: ReLU rectified linear unit function returns the input value for positive inputs and 0 for negative inputs. Leaky ReLU function is similar, but it adds a small slope for negative input values to prevent dead neurons. This means that leaky ReLU allows a small amount of the input signal to pass through even if the input is negative, whereas ReLU completely discards the negative input. This modification helps to prevent the vanishing gradient problem and allows the network to learn more complex patterns. What is the difference between the sigmoid function and the function used for regression tasks where the output will be continuous values? Answer: the sigmoid function is used for binary classification tasks where the output is a probability between 0 and 1. In contrast, the function used for regression tasks where the output is continuous is called the hyperbolic tangent tan function. The tan function provides both positive and negative results, whereas the sigmoid function only provides positive results. This makes the tan function more suitable for regression tasks where the output can be any real value. How do neural networks learn from the data? Answer: neural networks learn from data using a method called backpropagation during training. In this process, the network adjusts its weights and biases to minimize the difference between its predicted output and the actual output. The process starts with the input data passing through the network, generating an output. The cost function then compares this output to the actual output, and the backpropagation algorithm computes the gradient of the cost function with respect to the network's parameters. This gradient is then used to update the network's parameters using optimization algorithms such as stochastic gradient descent to minimize the loss. The goal is to adjust the weights and biases to minimize the cost function, allowing the network to learn from the data and make accurate predictions. How are the number of hidden layers and the number of neurons per hidden layer determined in a neural network? Answer: the number of hidden layers and the number of neurons per hidden layer in a neural network are typically chosen based on the complexity of the problem being solved and the desired level of model complexity. For simple problems, one hidden layer may be sufficient, while more complicated problems may require multiple hidden layers. The number of neurons per hidden layer can be determined by the number of input features and the desired level of model complexity. There is no one-size-fits-all solution, and the selection of these parameters often involves experimentation and validation to achieve the desired performance. It is also important to monitor the training and validation performance to detect overfitting and adjust the model accordingly. What is overfitting and how can it be avoided in machine learning? Answer: overfitting is a problem in machine learning where a model becomes too specialized to the training data, fitting the noise and unimportant patterns, and as a result, performs poorly on new unseen data. To avoid overfitting, several techniques can be used, including regularization, early stopping, data augmentation, and ensemble methods. Regularization involves adding a penalty term to the loss function to discourage large weights, while early stopping stops training when the model's performance on the validation set starts to degrade. Data augmentation involves generating more training data by applying transformations to the existing data, and ensemble methods combine the predictions of multiple models to reduce overfitting. By using these techniques, we can reduce the risk of overfitting and improve the generalization performance of our models. How can we reduce the risk of overfitting in a machine learning model? Answer: one way to reduce the risk of overfitting is to start with a simple model that has fewer layers and parameters. This can make it less likely for the model to overfit the training data. Additionally, we can progressively increase the complexity of the model until we achieve the desired performance. This approach can be beneficial in practical applications. What is regularization in machine learning, and how does it prevent overfitting? Answer: regularization is a technique used in machine learning to prevent overfitting of a model by adding a penalty term to the model's objective function. This penalty term imposes a constraint on the model's weights, making it more difficult for the model to learn complex patterns in the training data. As a result, the model is forced to generalize better and avoid overfitting, which occurs when a model becomes too specialized to the training data and fails to perform well on new, unseen data. By using regularization, machine learning models can be made more robust and accurate in the predictions. What is the main difference between loan and L2 regularization in neural networks? Answer: loan regularization, also known as lesser regularization, tends to set many model weights to 0, resulting in a sparse model. On the other hand, L2 regularization, also known as ridge regularization, constrains the magnitude of the model weights but does not set them to 0. This means that loan regularization can lead to a more interpretable model with fewer weights, while L4 regularization can help to prevent overfitting by reducing the magnitude of the weights. What is dropout and how is it typically used in neural networks? Answer: dropout is a technique used in neural networks to prevent overfitting by randomly dropping out or disabling some of the neurons during training. It is applied after the activation functions of the hidden layer, and typically it is set to a small value like 0.200. This means that during training, 20% or 0% of the neurons are randomly dropped out, respectively, which helps to reduce the model's reliance on individual neurons and improves its ability to generalize to new data. What happens to each neuron in the previously hidden layer when the dropout value is set to 0.20? Answer: when the dropout value is set to 0.20, each neuron in the previously hidden layer has a 20% chance of being inactive during the training process. This means that 20% of the neurons will be randomly selected and their outputs will be ignored, which helps prevent overfitting and improves the model's generalization ability. What is max norm regularization, and how does it constrain the weights in a neural network? Answer: max norm regularization is a technique used to constrain the magnitude of the weights in a neural network. It sets a maximum limit or norm on the weights of the neurons, ensuring that their values cannot exceed this limit. This helps to prevent the weights from growing too large and causing the network to become unstable or overfit the training data. By limiting the magnitude of the weights, max norm regularization encourages the network to learn more robust and generalizable features, which can improve its overall performance. What is the purpose of data augmentation in machine learning? Answer: data augmentation is a technique used to improve the robustness of a machine learning model by applying various transformations, such as rotating or flipping images, to the training data. This helps the model learn to recognize patterns and features that are not sensitive to changes in the input data, making it more accurate and reliable. By doing so, data augmentation enables the model to generalize better to new, unseen data and become more robust to changes in the input data. What is the benefit of increasing the amount of training data in a machine learning model? Answer: increasing the amount of training data provides the model with a diverse set of examples to learn from, which can help prevent overfitting. This is because a larger dataset allows the model to learn more general patterns and rules, rather than being overly specialized to a specific set of training data. As a result, the model is less likely to make errors when applied to new, unseen data. What is early stopping in machine learning, and how does it work? Answer: early stopping is a technique used in machine learning to prevent overfitting. It involves monitoring the model's performance on a validation set during training and stopping the training process when the validation loss stops decreasing. This is done to prevent the model from overfitting to the training data and to improve its generalization performance on new, unseen data. In other words, early stopping helps the model to stop learning when it starts to memorize the training data and becomes less effective in making accurate predictions on new data. By stopping the training process when the validation loss stops decreasing, early stopping ensures that the model is not overfitting and is more likely to generalize well to new data. Define epoch, iterations, and batches in the context of deep learning model training. Answer: in deep learning model training, an epoch refers to a complete cycle of training the model using the entire training dataset. An iteration, on the other hand, is the process of running a batch of data through the model, calculating the loss, and adjusting the model's parameters. A batch is a subset of the training data used to update the model's weights during training. The batch size is a hyperparameter that determines the number of iterations per epoch, and it's always less than the total number of training samples. The model analyzes each batch sequentially, one at a time, throughout each epoch, and the performance can be assessed on the validation dataset after each epoch. Define the learning rate in deep learning. Answer: the learning rate in deep learning is a hyperparameter that controls how frequently the optimizer adjusts the neural network's weights during training. It determines the step size to which the optimizer updates the model parameters with respect to the loss function, aiming to minimize losses and achieve optimal model performance. A high learning rate can lead to fast convergence but may also cause overshooting, while a low learning rate may result in slower convergence but potentially more accurate solutions. Choosing the appropriate learning rate is essential for successful deep neural network training. What is the cross-entropy loss function? Answer: the cross-entropy loss function is a widely used loss function in deep learning for classification problems. It measures the difference between the actual probability distribution of the classes and the predicted probability distribution. The formula for the cross-entropy loss function is given by y equals some sin k log ik, where y and y are actual and predicted values for a single instance. K represents a particular class, and k is the total number of classes. This loss function helps to optimize the model's performance by minimizing the difference between the actual and predicted probabilities. What is gradient descent and how does it work in machine learning? Answer: gradient descent is a method used in machine learning to minimize the cost or loss function by iteratively adjusting the model parameters such as weights and biases. It works by finding the direction of the steepest descent of the cost function, which is represented by the gradient. The gradient is a partial derivative of the cost function with respect to its model parameters. The model's parameters are then updated in the direction of the negative gradient, with the magnitude of the update determined by the learning rate. This process is repeated until the cost function is minimized, resulting in a better performing model. In simple terms, gradient descent helps the model learn from its mistakes by adjusting its parameters to reduce the difference between its predicted output and the actual output. How do you optimize a deep learning model? Answer: to optimize a deep learning model, you can try several methods. First, you can choose the right architecture for your model, which means selecting the right combination of layers and their parameters. Next, you can adjust the learning rate, which is the rate at which the model learns from the data. You can also use regularization techniques to prevent the model from overfitting, which means becoming too specialized to the training data. Additionally, you can use data augmentation to increase the size of the training dataset, transfer learning to use a pre-trained model as a starting point, and hyperparameter tuning to fine-tune the model's performance. By trying out these methods, you can optimize your deep learning model to achieve better performance on a particular task. What are batch, stochastic, and mini-batch gradient descent, and how do they differ? Answer: batch gradient descent is a method that updates model parameters using the entire training data set at each iteration. Stochastic gradient descent, on the other hand, updates parameters using only one training example at a time. Mini-batch gradient descent is a compromise between the two, where a small batch of training examples is used to compute the gradient and update parameters. This approach can be faster than batch gradient descent and less noisy than stochastic gradient descent, making it a popular choice in many machine learning applications. What are the different types of neural networks? Answer: there are several types of neural networks used in deep learning, including feed-forward neural networks, recurrent neural networks (RNN), convolutional neural networks (CNN), autoencoders, generative adversarial networks (GAN), and long short-term memory (LSTM) networks. Each type of neural network is designed to solve specific problems and has its own unique characteristics. For example, feed-forward neural networks are used for classification and regression tasks, while RNN are used for processing sequential data. CNN are used for image and video processing, and GAN are used for generating new data that resembles existing data. LSTM networks are used for modeling time series data and making predictions. Understanding the different types of neural networks is important for choosing the right architecture for a specific problem and achieving good results. What is a feed-forward neural network (FFNN)? Answer: a feed-forward neural network (FFNN) is a type of artificial neural network where the information flows only in one direction, from the input layer to the output layer, without any feedback loops. In other words, the output from one layer is used as the input to the next layer, and the process continues until the output is generated. This type of network is also known as a multi-layer perceptron (MLP) because it consists of multiple layers of interconnected nodes or neurons. FFNNs are widely used in many applications, including image and speech recognition, natural language processing, and regression analysis. They are particularly useful when the relationship between the input and output variables is complex and nonlinear. What is a convolutional neural network (CNN) and how does it work? Answer: a convolutional neural network (CNN) is a type of neural network that is designed to process data with grid-like topology, such as images. It works by using a series of convolutional and pooling layers to extract features from the input data. The convolutional layers use filters to scan the input data and detect patterns, while the pooling layers downsample the data to reduce the number of parameters and improve the network's ability to generalize. The output of the convolutional and pooling layers is then passed through fully connected layers to make predictions. CNN are commonly used for image classification, object detection, and image segmentation tasks. They are particularly effective at recognizing patterns in data that have a grid-like structure, such as images of faces, objects, and scenes. What is a recurrent neural network (RNN) and how does it differ from a traditional feed-forward neural network? Answer: a recurrent neural network (RNN) is a type of neural network that is designed to handle sequential data such as speech, text, or time series data. Unlike traditional feed-forward neural networks, which process data in a one-way flow, RNN allow information to be passed from one time step to the next, enabling the network to capture temporal dependencies and relationships in the data. This is achieved through the use of recurrent connections, which allow the network to maintain an internal state or memory of previous inputs. This internal state is updated at each time step, allowing the network to learn patterns and relationships in the data that are not possible with traditional feed-forward networks. RNN are particularly useful for tasks such as language modeling, speech recognition, and time series forecasting, where the input data has a temporal structure. What are long short-term memory networks (LSTMs) and how do they help in addressing the vanishing gradient problem in recurrent neural networks? Answer: long short-term memory networks (LSTMs) are a type of recurrent neural network RNN architecture designed to address the vanishing gradient problem. This problem occurs when the gradients used to update the network's weights become smaller as they are backpropagated through time, making it difficult for the network to learn long-term dependencies. LSTMs use three primary components: the memory cell, the input gate, and the output gate. The memory cell allows the network to store information for a long period, while the input and output gates control the flow of information in and out of the memory cell. This architecture enables LSTMs to selectively forget or remember information, allowing them to learn long-term dependencies and overcome the vanishing gradient problem, making them more effective in modeling sequential data. What is a gated recurrent unit (GRU), and how does it differ from a traditional recurrent neural network (RNN)? Answer: a gated recurrent unit GRU is a type of recurrent neural network RNN that is designed to handle the vanishing gradient problem, which occurs when the gradients of the error signal are multiplied together each time step, causing the model to forget information over time. Unlike traditional RNN, GRU use two gates, the reset gate and the update gate. The reset gate determines what information to forget, and the update gate determines what new information to add. This allows GRU to selectively focus on relevant information and ignore irrelevant information, making them more efficient and effective for modeling sequential data. In contrast, traditional RNN use a single gate to control the flow of information, which can lead to the vanishing gradient problem. GRU are particularly useful for tasks such as language modeling, speech recognition, and machine translation. What is an autoencoder neural network? Answer: an autoencoder neural network is a type of neural network that is trained to copy its input to its output. It is a self-supervised learning method where the network is trained on its own input data. The network consists of an encoder and a decoder. The encoder maps the input data to a lower dimensional representation, and the decoder maps this representation back to the original input data. The goal of the network is to minimize the difference between the input and output, which is typically measured by a loss function such as mean squared area or cross entropy. Autoencoders are often used for dimensionality reduction, anomaly detection, and generative modeling. They can also be used as a pre-training step for other neural networks, such as convolutional neural networks CNN or recurrent neural networks RNN. What is the attention mechanism in deep learning? Answer: the attention mechanism is a technique used in deep learning to help the model focus on specific parts of the input data that are relevant to the task at hand. This is particularly useful when dealing with long sequences of data, such as sentences or paragraphs, where the model needs to weigh the importance of each word or token when making predictions. The attention mechanism works by calculating a weighted sum of the input data, where the weights are learned during training and represent the model's attention to each part of the input. This allows the model to selectively focus on the most important information and ignore the rest, leading to improved performance and more accurate predictions. What is a generative adversarial network GAN, and how does it work? Answer: a generative adversarial network GAN is a type of deep learning algorithm that generates new, synthetic data that resembles existing data. It consists of two neural networks, a generator and a discriminator. The generator creates new data samples, while the discriminator evaluates the generated samples and tells the generator whether they are realistic or not. The generator and discriminator compete with each other, with the generator trying to produce more realistic samples and the discriminator trying to correctly identify the generated samples. Through this adversarial process, the generator improves its ability to produce realistic data, and the discriminator becomes better at distinguishing between real and generated data. Over time, the generator produces high-quality, realistic data that is often indistinguishable from real data. GAN have many applications, including image and video generation, data augmentation, and style transfer.